So once again, a brief you about this different transformation very fastly. In general, you have to remember at low temperature, the microstructure or phase in steel is is alpha iron. It is also referred as a ferrite. Alpha iron Fe is in BCC. So that is up to 912 degrees Celsius. It is in BCC. If you heat the steel above 912 degrees Celsius, so your BCC structure is transformed to FCC structure. Then that particular phase, or it is also referred as the equilibrium phase, is referred as the gamma phase. In gamma phase, it is again solid solution of Fe and iron. Fe is in one minute. So Fe is in FCC, Fe in FCC structure. Then if we heat the steel above 1392 degrees Celsius, there is one more allotropic transformation. That is nothing but it is FCC structure is transformed to the BCC structure. That particular iron is referred as the delta iron. So at very high temperature, below melting point temperature, the iron steel is existing in the BCC form Fe. Between 912 1392, Fe is existing in the FCC form. That low temperature below 912 degrees Celsius, it exists in the BCC form. So now austenite, it is also referred as a gamma iron. Then I am pointing towards this. The maximum solubility of gamma iron, the maximum solubility of carbon in gamma iron is 2.11. That is 1147 degrees Celsius. Now you have to see the iron carbon diagram. You have to identify 1147 degrees Celsius and 2.11 degrees Celsius. That is maximum solubility of gamma iron is 2.11. Then one more is austenite. So now austenite is FCC structure, already we have discussed, and maximum it will exist up to 723 degrees Celsius. There is one more is ferrite. That is nothing but alpha iron. The maximum solubility is 0.02. Let it be 0.02%. Again, you should be able to identify 0.02% in iron carbon diagram. Then 723 degree also you should be able to mark in iron carbon. So one more is delta iron. Maximum solubility of carbon is 0.1%. Again, that's you should be able to write it in iron carbon diagram. Again, these are things are required for your heat treatment. And it is existing at 1493 degrees Celsius. Then pearlite, it is a combination of cementite and ferrite. Cementite is Fe3C. The ferrite is it is nothing but alpha iron. This is a microstructure. Now this is now we can identify the maximum solubility of gamma is 1148 degree or 1149 degrees Celsius. That is 2.1% of carbon. That maximum amount of carbon present in gamma iron is 2.1. That you have to remember. Then maximum solubility of alpha iron, maximum amount of carbon that may be present in the alpha iron is 0.02%. I told you to practice this iron carbon diagram, then only you can understand better. Otherwise, if you don't practice, so what you covered in the last class, then it is very difficult to understand. Then there is a important reaction. One is eutectic reaction. The liquid is transformed to two solid. It is happening in the cast iron region. So one is gamma plus Fe3C. One is gamma phase and one more is Fe3 phase. So that together we are referring as a leduburite. The leduburite is gamma plus Fe3C. We have one more solid or solid phase alpha plus Fe3, that is pearlite. Corresponding reaction is eutectoid reaction. eutectide reaction takes place. Again, you have to remember the temperature, 727 degrees Celsius, and percentage of carbon is 0.8. Eutectic reaction, temperature is 1148 degrees Celsius. Corresponding percentage of carbon is 4.33. So one more is peritectoid reaction. That percent reaction takes place at 0.18% of carbon and temperature is 1495 degrees. These are the important point you have to remember in iron carbon diagram. Then if the percentage of carbon is more than 2.11 or 2.1, so then it belongs to cast iron. We have Fe and carbon alloy, and if the percentage of carbon is 2.11, then it comes under cast iron. Then again, cast iron, there are two types of cast iron depending upon eutectic composition. If the percentage of carbon is less than eutectic composition, then it is referred as a hypoeutectoid steel. Can you see the iron carbon diagram? So now percentage of carbon is more than 4.33, then it is referred as hypereutectic steel. So everything is decided by hypereutectic cast iron. If it is less than eutectic composition, it is hypoeutectic cast iron. If it is more than eutectic composition, that is 4.33% of carbon, then it is referred as a hypereutectic cast iron. Again, steel can be classified into two types of steel based on eutectoid reaction. If the percentage of carbon is less than 0.8, then it is referred as a hypoeutectoid steel. If the percentage of carbon is more than 0.8, then it is referred as a hypereutectoid steel. In the steel, eutectoid reaction takes place. In cast iron, eutectic reaction takes place. Again, in steel, at higher temperature, there is one more transformation takes place. That is nothing but peritectic reaction. Do you have any doubt in iron carbon diagram? If you don't have the doubt, then heat treatment and remaining topic will be easy for you. If you have any doubt, you can clarify me. Otherwise, there are some more simple slides. So we have one more slide. Is it PPT is visible? Yes or no?
Yes, sir.
Okay. So this is a separate reaction in because if you see the complete iron carbon diagram, it may not clearly visible. I have putting some more slide so that it will identify only the reactions. There are two ways in the examination they ask the question. So one is draw the neat sketch of the iron carbon diagram and mark salient temperature and composition. You have to mark the temperature as well as composition for the different reaction. Sometimes they may ask you to explain eutectide and eutectic reaction with respect to iron carbon diagram or peritectic reaction in the iron carbon diagram. Then you have to draw only the part of the iron carbon diagram you can explain. Now, complete steel can be classified into two categories. One is hypoeutectoid steel. So one more is hypereutectoid steel. You can say the eutectoid. Hello.
Excuse me, sir.
Tell me.
So for this iron carbon phase diagram, so there is any procedure like process through which we draw the diagram, or we should learn this entire diagram for exam?
First, you have to understand the concept behind iron carbon diagram. That's the first part. Then you have to practice this. Your referring points means you practice that particular diagram around 2 to 3, or at least 2 times. Then try to remember the 3 important reactions. One is peritectic, one more is eutectide and eutectic reaction. Then other things, if you know those 3 reactions and corresponding composition and corresponding temperature, all those points you have to remember. Some aspect you have to remember. Some fundamentals, if you know those whatever we are discussing from the last 3 to 4, then writing it will be easy.
So the temperature, like melting point of carbon and of iron and the
All
TE, we
those
should
things,
remember all
some
those.
of the important, like the 912 degrees Celsius, depending upon this, there may be slight difference. Here, this 912 degrees Celsius you have to mark. This 727 degrees required. Then this maximum solubility of alpha in this carbon in all this alpha is important, 0.02%. This 0.8 is required. Those are the important parameter. Is it there? One complete iron carbon diagram you are, I think I told you are referring, I think, Panish textbook. The all composition, temperature, everything is there. Just you have to write. So if you write major temperature and important key point, not each and everything, some amount of remembering is also required here, especially for iron carbon diagram. But if you study this diagram separately, then drawing the iron carbon diagram will be easy. I hope I clarified your doubt.
Yes, sir. Yes.
Because this, especially from the, I am teaching this subject for many years, more than 10 years. So students will face in iron carbon diagram, we don't and heat treatment. Earlier days there is a unit scheme. Unit scheme is there are 8 units and 8 questions. Out of 8, the student used to have to write the 5 questions, choosing any 5. It is not like a model scheme or a unit scheme. 8 unit, 8 chapters. Then students have the choice for studying only 5 module. Most of the time, students will not study, were not studying this iron carbon diagram. That is a one separate unit, and heat treatment is one more unit. They are not used to study that because they feel little bit difficulty. But now it is a module scheme. There is no option. You have to study both iron carbon diagram as well as heat treatment. Now this diagram very you can understand. This we have solid. It's a transformation. Instead of saying a reaction, it's a transformation. We have the solid. It is austenite. It is transformed to two solid phases. One is alpha phase and one more is Fe3 phase. Together it is referred as the perlite. It is perlite. You can see here alpha plus Fe3. Don't add. It is not like a mathematics. Don't think that alpha plus alpha is a separate phase. The cementate is also separate phase. I have some more this actual photograph, then you can understand. So now there is one more peritectic reaction. This particular reaction takes place at 1493 degrees Celsius. We have molten metal of iron and the solid. Solid is nothing but a delta iron. It transformed to one more solid. With respect to iron carbon diagram, it is gamma. So this is a peritectic reaction. It is enlarged view. You can see we have molten metal of steel plus delta iron. So this particular reaction takes place at, I think, what is the temperature? This is 1493 degrees Celsius. 1493 degrees Celsius. And composition is 0.18. Only this particular temperature, this particular composition, peritectic reaction takes place. Now you can see this is the perlite. This is the microstructure of the perlite. There is an alternate layer of alpha. One layer is alpha and one more layer is Fe3C. That is simple way to understand. I am showing this. There is a eutectic reaction already we discussed. This is a complete iron carbon diagram, colorful diagram. You can see you have the layer, different layers. This is a part of iron carbon diagram. We have the transformation, especially in ferrite. We have ferrite is nothing but alpha iron. It is a BCC. Austenite is a FCC. You can see the whole complete atomic arrangement changes. Whenever there is a change in temperature, the complete atomic rearrangement of the atoms will take place. So that's why you can see here. We have body centered Fe, unit cell. When it comes here, we have phase centered Fe. And here it is a complete cementate is an intermetallic compound. It is a metastable. Metastable means suppose some amount of cementate is there in steel. If you use the steel for over a period of time, then it may transform into some more reaction like only Fe3 plus the carbon, there is a further transformation maybe takes place. So now this is eutectoid steel, 0.8%. So eutectoid steel, the final product in the sense the microstructure, it is the perlite. This is the perlite. This is the actual microstructure. You can imagine perlite. We have a alternate layer. One is dark layer, one more is light layer. The one layer is Fe3C and one more layer is the alpha. You can see this is the actual microstructure for eutectoid reaction. Then hypoeutectoid steel, if the percentages of the carbon is less than the eutectoid composition 0.8, then we can see here, whenever there is a change in composition, we can see the complete microstructure. Whether it is a 0.8 or 0.8% or 1.5% of the carbon in the steel, by external appearance, it almost all steel looks like same. But only internal microstructure, we can distinguish what is the percentage of carbon. Here, most of the automotive companies, aerospace companies, whenever they are receiving the steel, they will not see only the weight of the steel. Few tons, they will go to weigh it, then they will not that is one part of the checking. Another part is randomly they will pick some steel material, they will see the microstructure. Based on that, they will accept the complete truckload of steel, otherwise they will reject. So most of the time, even Bosch also, they have a separate microstructure division. Even Toyota, most of the industries, so they have separate division, or sometimes they'll outsource this component because they don't have sophisticated facility, especially for small scale industries and medium scale industry. So there are many agencies, they'll take care of studying the microstructure, they'll give the microstructure, and they'll send the sample to the industry, small industries or small consultancy services. They'll see the microstructure, they'll send it back. Based on that, they'll accept or reject the component. So now this is if it is hypoeutectoid steel, which is 0.4%, we can see the difference. If it is hypoeutectic cast iron, this is the microstructure of the cast iron. If the percentage of the carbon is 2.1, more than 2.1, window in the door. If the percentage of carbon is more than 2.1, then it comes under cast iron. Within the cast iron, there are two types of cast iron. So one is hypoeutectic cast iron, and one more is hypereutectic cast iron. Eutectic composition is 4.33. Eutectic reaction takes place in the cast iron region in the iron carbon diagram. So these are the simple way to remember, because if you know those things, then writing the iron carbon diagram is easy. Eutectic reaction takes place in cast iron region, and eutectoid reaction takes place in steel region of iron carbon diagram. So now this is one more micrograph, actual cast iron. If the percentage of carbon is more and more, so then it will form the cementite. These dark spots are nothing but a cementite, because if there is a more amount of carbon and Fe will join, it will form new compound, not new phase, new compound. It is not a solid solution. Fe3 is not a solid solution. Alpha iron is the solid solution. Delta iron is the solid solution. Then your gamma iron is also solid solution. But Fe3 is compound is formed because the bonding, atomic bonding, Fe3 compound is formed. So now if the percentage is very high, then you'll get these are the different percentage of carbon. We can see here. So perlite, this is a perlite structure. How perlite is formed? We have austenite solid. It is a solid. Austenite is a solid. It's a FCC structure. During the cooling process, so carbon atoms move towards this. So we have cementite and alpha. So cementite and alpha. We will get over a period of time during the solidification process. Now already it is solidified. Austenite is already solidified. It is a solid one. If you decrease the temperature, so during the process of decreasing the temperature or cooling process, so it will form alternate layer of Fe3C and alpha. You can see alternate layer of Fe3C and alpha. So now you can see the perlite, we have ferrite. Ferrite is nothing but alpha. There is a perlite, it is alpha plus Fe3C. Then cementite plus ferrite, that is comes on the right side part of the iron carbon diagram. Cementite, because on the right side there is a more amount of carbon. The carbon will join with Fe atom and it will form intermetallic compound, that is nothing but Fe3C. That comes on the right side of the iron carbon diagram. So now you can see we have FCC structure, how it is transformed to BCC structure. This is the FCC structure. At the midpoint of the FCC structure, this is a rearrangement of the atom. It is not like a magic. During solidification, within the solid state, the atoms will move. Because of the movement of the atom, the atoms will rearrange themselves. Either it will transform from FCC to BCC or BCC to FCC, depending upon whether you are cooling the steel, the solid steel, other we are heating the solid steel. Now we can see here during this process, we will get alpha, ferrite will get alpha. This is a solidification process. So now if you once you understood, then we'll go to straight away, we'll go to the cooling curve. Already we have discussed. So we have drawn iron carbon diagram. Y-axis of the iron carbon diagram is, it is a phase diagram, is temperature. X-axis is percentage of carbon. It is a iron carbon equilibrium diagram. Once you say it is a equilibrium diagram, the cooling is taking place very, very slowly. Imagine you have the molten metal. From molten metal to the room temperature, the cooling takes place very, very slow cooling. Then only it is known as the equilibrium process. If the cooling is fast, then you cannot say it is a equilibrium process. Cooling is very, very slow. It is almost like a quasi-static. Suppose the temperature decreasing from around 900 degrees Celsius to 899 degrees Celsius, it may take hours together because it is a very, very slow cooling process. And then only we can say that it is a quasi-static process or equilibrium process. That iron carbon diagram already was studied, is a part of phase diagram. Y-axis temperature, X-axis.
Sir, the screen is not seen, sir.
Oh, okay. Because I moved to one more slide. If that set of cases, you have to inform me. Anyhow, I'm not reading straight away from this one. So we finished the phase diagram. And especially the iron carbon diagram is very, very important for complete one module, that is heat treatment process. Y-axis represent temperature, X-axis represent percentage of the alloying element or the base metal, whatever it may be. Now, when you come to the non-equilibrium diagram or cooling curves, cooling curve is you are cooling very fastly, not very, very slowly. It is not an equilibrium cooling process. It is a non-equilibrium cooling process or non-equilibrium heating process. To understand those processes, the most of the practical cases, it is a non-equilibrium process. Once you pour the molten metal into the mold, the cooling takes place very, very fastly. And center part of the mold, the cooling may take place very, very slowly, but surround the mold or the molten metal very close to the mold. So it is solidified first, then solidification front moves toward the center of the mold. So in most of the practical cases, it is not an equilibrium cooling or heating process. It is non-equilibrium process. To understand that, we have to study one more diagram, that is referred as the cooling curve. It is also referred as the temperature time transformation diagram. So y-axis represents temperature. Instead of x-axis composition, so you are writing time. with respect to time, how phase changes. That is very important. Same thing is explained here. We are said referring as. I hope PPT is visible now. Yes or no?
Yes, sir.
Yes, sir.
Okay. Now you are talking about the time temperature transformation diagram. It is also referred as a TTT or triple T diagram. It is also referred as isothermal transformation. What is meant by isothermal? So isothermal means the complete transformation takes place at constant temperature. We have austenite, we have eutectide reaction. Now we are not worried about the eutectic reaction in the iron carbon diagram. Now, when you come to your heat treatment, you are talking most of the time, you are concentrating only on eutectide reaction. Eutectide composition is 0.8, and eutectide reaction takes place at 727 degrees Celsius. So eutectide reaction, you have gamma or austenite. Austenite is transformed to perlite. Austenite is gamma, it is transformed to perlite. It is nothing but alpha plus Fe3C. We have the transformation. This complete transformation takes place at constant temperature. So then it is referred as a isothermal transformation. It is also referred as a Bain's curve, because one of the scientists who developed this TTT diagram, hence it is referred as a Bain's curve. It is also referred as a C curve or S curve because the shape of the curve almost resembles C curve. So what is x-axis TTT diagram? The x-axis is time, the y-axis is temperature. Now, how you have to draw the TTT diagram? TTT diagram means because different temperature, there's different cooling. This is a normal heat treatment process itself. In the heat treatment process, I'm talking about the steel. First, you have to heat the material above lower critical temperature. You have to remember, now I am using the one more term. It is a lower critical temperature. It is also referred as A1 line in your iron carbon diagram. I'll show it later. Once you say lower critical temperature, it is nothing but your eutectoid temperature. The eutectoid temperature for the steel is 727 degrees Celsius, and corresponding the composition is 0.8. First, you have to heat the steel material above 727 degrees Celsius. So then only transformation takes place, like your degree courses. If you get minimum of 40% of the mark, if the percentage is more than 40 or more than 35, so then only you are moved from one semester to the next semester. Or if the percentage is more than 60, then only you are declared as a first class. That is the minimum cutoff mark will be there. In the similar way, so only once if you heat the steel above 727 degrees Celsius, then only will get the transformation. Otherwise, no transformation. Like students will come to the college, they'll enjoy, they're going back. There is no moving from lower semester to the higher semester. Same thing will happen to the steel. The temperature increases from, let it be around 30 degree to 700 degrees Celsius. So then if you imagine, suppose you are cooling it, so there is no transformation from austenite to any transformation, just metal will get heated, then it will cool down, then there is no change in microstructure. We can say that there is no change in microstructure. The microstructure remains same. That's why. So when steel is heated to, even we have stove, even some utensil, etc., for preparation of coffee, tea, etc., there may be steel. But there, even though you are heating it, there is no transformation because your heating temperature is below lower critical temperature. That line is referred as A1 line. For the steel, it is 727 degrees Celsius. Even in empty lab also, you are heating the steel above 727 degrees Celsius. That's a minimum requirement. So that means once you heat the steel above 727 degrees Celsius, we have alpha iron. Alpha iron is also referred as a ferrite. So ferrite is transformed to the austenite. Your eutectide reaction takes place only when if the temperature is above 727 degrees Celsius. Complete steel material should be in the austenitic temperature. It is also referred to the austenizing temperature. This is a transformation temperature. Your steel is transformed from the perlite or your ferrite to austenite, hence it is referred as austenizing temperature. So now once you heat it to the 727 degrees Celsius, only the surface of the steel may be 727 degrees Celsius. But what about inside core part? Imagine thickness of the steel is around 10 centimeter. Surface temperature may be 727 degrees Celsius. The core part of the steel may be only 500 degrees Celsius. Like your flame hardening, what you are doing in your the surface heat treatment, you are heating only the surface of the steel by using flame, oxyacetylene flame, or some induction coil. But you have to keep the whole steel in the austenitic phase only, complete inside core part as well as outer surface, because we are going for the volume heat treatment or bulk heat treatment. Whole volume of the steel is transformed to the austenite. So that's why you have to keep it for a long period of time. After 727 degrees Celsius, you cannot stop the furnace. Temperature is set for 727 degrees Celsius. You have to keep this particular material for around half an hour, 45 minutes, depending upon the thickness of steel. Then only complete the whole volume of the steel temperature is above 727 degrees Celsius, or complete volume of the steel, it is only austenitic phase. Now you are heating above 727 degrees Celsius, such a way that complete phase is only austenite. Otherwise, there may be small amount of perlite, some amount of austenitic, or some amount of ferrite may be there. Then you have to cool it. It is an equilibrium cooling process. What is meant by equilibrium cooling process here? What is meant by equilibrium cooling process? Or isothermal process? So isothermal process means we have the salt bath. You have to the complete transformation from austenite to the perlite. Instead of saying alpha plus Fe3C, I am now onwards I am saying perlite. Once you say perlite, you have to remember it consists of the alpha plus Fe3 is nothing but a perlite. Now I don't use alpha plus Fe3C. Now I am using the perlite. There is a transformation from austenite to perlite. So that transformation takes place at constant temperature. So for that we require you have to keep the metal in the constant temperature. So it is the below 727 degrees Celsius. So now when austenite temperature is below 727 degrees Celsius, it is referred as the unstable austenite. When they are stable, we cannot change. There is no transformation takes place when they are stable. When they are unstable, then only the lot of transformation takes place. So now you are keeping the complete steel rod in the salt bath. In this salt bath, you are maintaining below 700 degrees Celsius. So if you keep it for half an hour or 1 hour, depending upon the size of the component, your austenite is completely transformed to the perlite. How much time it takes, that will be explained by your TTT diagram. Then afterwards, you have to go for conventional quenching process or cooling process. So this is the foundation for understanding TTT diagram. Now we come to TTT diagram. So now x-axis refers to temperature, not temperature, the time. So y-axis represent temperature. So you are starting from the austenite. You are heating the steel above 727 degrees Celsius. Repeatedly, I am saying the iron carbon diagram. One reaction takes place, that is eutectoid reaction. So above the eutectoid temperature, it is only austenite. We can see here we have one horizontal line. So it is austenite. Above 727 degrees Celsius, it is a stable austenite. If you keep the steel above 727 degrees Celsius, austenite will be stable. If you decrease the temperature, so austenite will not be stable, and it will be unstable. There may be transformation from austenite to perlite. So we can see here below 727 degrees Celsius, austenite is transformed to the perlite. There is a nose part of this S curve or C curve. This nose part of the curve or the temperature is 550 degrees Celsius. we can divide the complete your TTT diagram into 3 zones. The bottommost zone, that is the shaded zone, there is only one type of microstructure, that is martensite. This region is only martensite, some amount of austenite. Between 240 degrees Celsius to 550 degrees Celsius, this temperature you have to remember, 240 degrees and one more is 550. That important temperature I'm telling. 3 temperature you have to remember. One is 240, one more is 550, and one more is 727 degrees Celsius. Between 550 and 727 degrees Celsius, austenite is unstable. If you keep the salt bath, I'm talking now, I will coming back. If the salt bath temperature is 700 degrees Celsius, see here, suppose you are maintaining the salt bath at 700 degrees Celsius, there is a transformation from austenite to perlite. Because austenite is unstable, only when they are unstable, there may be some transformation process. So some austenite to perlite takes place. Austenite is given by gamma. Gamma is transformed to alpha plus Fe3C at constant temperature. If the temperature is very high, high in the sense very close to 727 degrees Celsius, then microstructure is coarse. Coarse means size of the grain is bigger and bigger. If the temperature is very close to 550 degrees Celsius, or let it be around 600 degrees Celsius, again it is a perlite only. The microstructure is very, very small. It's a fine microstructure. Already you have seen the microstructure. The size of the grain is very, very small. Then it is referred as a fine perlite. So instead of keeping the salt bath at above 550 degrees Celsius, if you keep the salt bath at 400 degrees Celsius, now you can go back and see. Instead of keeping the salt bath at 700 degrees Celsius, if you keep the salt bath at 400 degrees Celsius, you can see here. If you are keeping the salt bath at 400 degrees Celsius, so we have the iron rod, it is already heated, steel rod, it is already heated. You are maintaining the steel rod at only at 400 degrees Celsius for a long duration. For that, you are dipping into the salt bath. The salt bath temperature you are maintaining around 400 degrees Celsius. Now there is an austenite. Same austenite is transformed to one more compound. So that compound is referred as a bainite, because Bain is the scientist who got the first time he developed this particular microstructure. So hence it is referred as a bainite microstructure. So we have upper bainite and lower bainite. If you keep the temperature around 500 degrees Celsius, you will get one more bainite is again alpha plus Fe3C only. Don't confuse between perlite. Perlite is also alpha plus Fe3C. The bainite is also alpha plus Fe3C. The best example you can understand is, imagine there is one person, Lakshman. There is one more person also, Lakshman. Don't think that both are resemble same. One person may be very tall, one more person is very short. But both are Lakshman only. Like this, here also alpha plus Fe3C. The microstructure is totally different. The face look may be different. This alpha plus Fe3C, the microstructure is totally different. When you come to bainite, their microstructure is different, but still we have alpha plus Fe3C only. Don't think that, don't confuse. Here also alpha plus Fe3C, here also alpha plus Fe3C, but the microstructure are totally different. So this is referred as the isothermal transformation. This complete transformation takes place at constant temperature from austenite to perlite or austenite to bainite. Hence, it is referred as an isothermal transformation curve. It is an isothermal transformation curve. Suppose if you consider this particular point, it is around 4 seconds. So that means we have, if we keep at around 4 seconds, just transformation takes place. Imagine, so from 727 degrees Celsius, you cool down to 550 degrees Celsius or putting into the salt bath, which is maintained at 550 degrees Celsius. Within 4 seconds, your transformation takes place. This is a start of transformation. The leftmost curve is there. There are two curves. The shaded region, the leftmost curve is the start of transformation. Within a fraction of a second, complete transformation may not take place. So it will start of transformation. Then after 15 seconds, from 4 second to 4 second is the start of transformation time. And after 15 seconds, complete transformation takes place from austenite to perlite. That we can see. This complete left side is start of transformation. The right side curve is this curve is the end of transformation curve. Same diagram is available in the local books also. Even Panish has the same diagram is there. If you cool it very, very slowly. But if instead of if the cooling rate is very, very fast, what you have done is in your material testing laboratory without understanding the concept of heat treatment. So your metal is more red hot condition. It is 727 above 727 degrees Celsius. Your metal is 727 degrees Celsius. You cool it very fastly within 4 seconds. Within 4 seconds, it comes down to the room temperature. We don't get perlite. We don't get bainite. So we'll get one more microstructure. That microstructure is referred to the martensite. There is one more microstructure that is a martensite. That means if you cool it very, very fastly, if you dip into the water, so within 3 to 4 seconds, the temperature will come down to room temperature. We'll get one more the non-equilibrium phase of iron carbon system is the martensite. Bottommost region is the martensite. Now in the conclusion is, if you maintain the salt bath, above 550 degrees Celsius. Why I'm saying 550 degrees is, this is the nose part of the curve. This is 550 degrees Celsius. If you maintain the salt bath, this is real experiment. I'm talking about the real experiment now. If you maintain the salt bath above 550 degrees Celsius, the complete austenite is transformed to the perlite. If you maintain the same salt bath below 550 degrees Celsius, we can see here, below 550 degrees Celsius, then complete austenite is transformed to one more the solid phase, that is nothing but the bainite. We can see bainite. Depending upon the temperature, it may be upper bainite or lower bainite. But we can skip this also. What you done in your empty lab is, you are heated the steel above 727 degrees Celsius. Then you are not soaked. You are removed this process. The straight away you are quenched in the water. Quenching is nothing but a sudden cooling process. Most of the time you are putting into the water. We bypassed this stage. Then we'll get new microstructure, that is martensite. You are cooling the steel from 727 degrees Celsius to room temperature within 3 to 4 seconds. Then we'll get one more microstructure. It's a hardened microstructure. That's why you are studying the hardness of the steel before heat treatment. You are studying the hardness of the steel after heat treatment process. If you conduct the experiment correctly, then hardness will be increased, because you'll get the one more microstructure. This is a martensite. The martensite microstructure is the hardest microstructure or phase in your iron carbon diagram. I hope you understood. If you have any doubt, you can clarify about the cooling curve now. If you understand iron carbon diagram and cooling curve, then 50% of the heat treatment is very easy. Already you are discussed. Do you have any doubt about the cooling curve? Even these diagrams you have to practice. If you don't have any doubt, I'll go for one more curve. This is isothermal transformation curve, or is it isothermal? This is TTT diagram only, but it is only isothermal transformation. There is one more type of transformation. Now you can see this. PPT is visible now?
Yes, sir.
Okay. This is one more diagram. You can understand better. This is a colorful diagram. Now you are starting from 727 degrees Celsius. Then it has a transformation from austenite to the perlite. It may be a coarse or fine. Again, there is a transformation from austenite to upper bainite or lower bainite. If you go for air cooling, that means you are bypassing this part. So now we have a perlite microstructure as well as bainite microstructure. If you follow all three stages, Imagine I am removing this process. Already steel is heated around 727 degrees Celsius. Then, without putting into the salt bath, directly you are going for the air quenching or water quenching. Water quenching means directly you are putting outside the atmosphere, outside the furnace in open air. Then it is referred as air quenching. If you dip into the water, what he in our experiment, what he done is he put the specimen very close tap. Then it is automatically it is cooled down. So then we don't get perlite, we don't get bayonet. So then we get the martensite. We can see here it is a air cool, then water quenching, then we will get the martensite. The bottom portion is the martensite. We can get harder microstructure also. You can get the softer microstructure. During your heat treatment, we can make the material very soft also, or we can make the material very hard also. So now I am talking about the start of transformation and end of transformation. This leftmost red line refers to start of transformation from austenite to perlite or austenite to bayonet. And there is a dotted line here. Here there is a perlite as well as austenite. Here left side only austenite, here only perlite. In between, during the process of transformation, there may be both perlite as well as austenite in the transformation. Suppose instead of waiting for 20 minutes time is required from complete transformation from austenite to perlite. If you remove the component in between, then there may be only 50% austenite and another 50% only perlite. So now we are talking about the non-equilibrium phases of iron carbon diagram. Non-equilibrium phases means you are cooling it very fastly, or even medium cooling also comes under. Then we'll get three more microstructure. One is bayonet, one more is martensite, and one more is austenite. Austenite may be stable or unstable. That's it. Now we are talking about one more diagram. What is this diagram? It is a cooling curve. So if we have S curve, this is a TTT diagram. We have S curve or C curve. If you consider only this C curve, this is almost like a C. Then in the examination, they may ask for two cases, two type of question. One, they may ask only for draw TTT diagram. Once you say draw TTT diagram, you have to draw this diagram. If you are referring, most of them you are referring the textbook. You are not depending on the PPT, etc. This diagram is given. It is only the TTT diagram. It's an isothermal transformation diagram. But in the examination, they may ask for superimpose the TTT diagram with cooling curve. You have to superimpose. This is a TTT diagram. These are two S curve. So there are the curves here. These are the cooling curves. This is one cooling curve. This is one more cooling curve. We have around 5 to 6 cooling curve. So depending upon the cooling rate, you may get perlite, you may get bayonet, or you may get lower bayonet, or you may get martensite. Then it is nothing but overlapping of TTT diagram as well as your cooling curve. The first you will see the color, this color diagram, then you can understand better. You have the cooling curve. This C curve is the cooling curve. This is not cooling curve. It's a TTT diagram or isothermal diagram. You are superimposing the cooling curves. Imagine cooling is very, very slow. From 727 degrees Celsius, it starts from almost, let it be 1 second. To transform into the coarse perlite, we required around 10 to the power 4 seconds. 10 to the power 4 is almost 10,000 seconds. The total time required is very, very slow cooling, very, very slow cooling. Then we'll get one microstructure, that is nothing but a perlite. So that is nothing but an annealing process. There is a one heat treatment process. There is an annealing process. It is very, very slow cooling process. Then there is a, most of the time for annealing process, will not take out the component practical aspect. Yeah. So we don't take out the component from the furnace after reaching 727 degrees Celsius or above 727 degrees Celsius. We'll switch out the furnace. We don't take out the component from the furnace. Because once you take out the component from the furnace, the temperature comes down. To avoid that, you are keeping the component inside the furnace. The furnace door is closed. Just you are switching off the furnace. So that means, suppose today evening, today afternoon, you have conducted the experiment. You have heated the metal above 727 degrees Celsius, and you switched off the furnace. The door is closed still. If you come and tomorrow morning, if you open the furnace, or if you see the temperature of the temperature of the furnace may be around 200 or 300 degrees Celsius. Or temperature of the component is 200 to 300 degrees Celsius. To decrease the temperature from 800 degrees Celsius to 200 degrees Celsius, it took almost 10 to 12 hours. That is very, very slow cooling process. So then we'll get very fine microstructure. Because of the fine microstructure, ductility of the material is improved. So material can undergo huge amount of plastic deformation. You are talking about the strain. The deformation is 1 mm, or deformation is 5 mm, or deformation is 10 mm. Then maybe imagine you can take two types steel. One steel is very soft, one more steel is especially high carbon steel or tool steel, etc. There may be very harder because ductility is very, very less. So for fine perlite, if you cool it very, very slowly, we'll get one microstructure that is nothing but a coarse perlite. Then the steel is soft, it has good ductility. Then if you consider one more extreme cases, what you've done in a lab, empty lab, not only conducting few experiments, you have to understand the fundamental. You are heated the steel to the above 727 degrees Celsius. Then, so you are putting into the water, that is after the water quenching. So within almost a few seconds or microsecond, the temperature comes down from 727 degrees Celsius to almost 100 degrees Celsius or maybe around 50 degrees Celsius. Then it is very, very fast cooling. Then we get totally different microstructure. That is after the martensite. So once you get martensite microstructure, if you cool it very, very fastly, then hardness will be increases. That's a one more process. Instead of that, if you go for air cooling, that is the one more heat treatment process. That is nothing but a normalizing heat treatment process. You are taking out the component, you are putting in the atmosphere, open atmosphere. So from 727 degrees Celsius, it may come down to the room temperature after half an hour. Or if you after 10 minutes, you can just 10 minutes you touch, still it will be hot, very hot. After 1 hour also, you can touch the component just for testing. So it may be almost cool. It maybe comes to room temperature after 1 hour. That is a medium cooling. Then we'll get binetic microstructure. That particular heat treatment is referred as a normalizing heat treatment. Now there are three types of heat treatment. One is you are talking about the bulk heat treatment. Complete volume of the material is heat treated. One heat treatment is the annealing process, where cooling rate is very, very slow. Furnace cooling. So one more heat treatment process is cooling rate is medium or air cooling. That is referred as a normalizing heat treatment process. And one more heat treatment process is very, very fast. Cooling is very, very fast. These are the cooling curves. Cooling curve, very, very fast. And you are dipping into the water or some oil bath, which is maintained at room temperature. Then you'll get martensitic structure. That process is referred as a hardening process. That is the hardening process, the volume bulk hardening process. Now we can see three heat treatment. One is annealing, one more is normalizing, so one more is hardening process. Once you understand, then all the temperature, all procedure, everything is there in the book. But these are the concepts you have to understand. So anyhow, you will discuss this diagram because you have to still see this diagram. Or I'll explain this cooling curve in detail. But the simplest cooling curve I got it from net. So you can, these are the some more cooling curve. You can see here, furnace cooling will get perlite, air cooling will get binite, almost binite. If you cool it very fastly, you'll get ash tempering. One more process, you have to cool it very fastly, then you are keeping in oil bath for a long period of time, you get one more microstructure. Then if you cool it straight away, you get mart tempering or mart temperature. This martensite you will get. But these are some more diagram. So annealing, you already some concept you have studied. Very, very slow cooling. Normalizing, you can see here, normalizing is a little bit faster cooling. There are different types of annealings are there. But Armorizing, you are heating the material above A1 line. Again, this is a part of iron carbon diagram. Why I am showing is iron carbon diagram is very, very important. Left line is referred as A1. This is the ACM line. Your hardening process also is again as a part of your iron carbon diagram. To understand iron carbon diagram, you have to understand this. To understand heat treatment, you have to understand iron carbon diagram. To understand iron carbon diagram, you have to understand the phase diagram. There's a link. And why I'm showing this diagram is again tempering process. There is one more heat treatment process. Again, that should be explained with respect to iron carbon diagram only. Then there is one more heat treatment. There is a arc tempering. This arc tempering is explained with respect to TTT diagram, time temperature transformation diagram. The malt tempering is a one more heat treatment process. Again, that can be explained with respect to TTT diagram. Just read the book today itself. Practice those some of the TTT curves and cooling curves as well as iron carbon diagram. If you have any doubts, we can discuss tomorrow also. Tomorrow also I may take some class. Or if you have any doubt also, now also you can discuss. Those are not entered your USN number, you can enter your.
Sir, we are unable to enter the name and USN, sir. Please can you take oral attendance?
Which one?
Yes, sir.
Yes, sir.
Actually,
We are
chat
unable
box
to
not
enter name and USN in the chat box.
Today only. Your problem is only today.
Today.
Yes, sir.
Today it has problem, I think. Okay, I think people 25.
Please take attendance, sir.
Chart can't available at this time. Okay. Just I'll call your attendance.
Okay,
Yes,
sir.
sir.
Calling your attendance is very easy to take the attendance. Otherwise, I have to look into your chart box. But only problem is yours. Anyhow, this is a